Yeah, Evgeny, please start.
I hope. Hi. I hope everyone sees my screen, and if you have any questions, please use raise your hand function in Zoom. And so today I'm talking about cryptographic hash functions. This is probably the most widely used cryptographic primitive in NEAR. We have many data structures, mostly Merkle trees, but but also some other that are using them. So what is a cryptographic hash function? It is a function from strings of arbitrary lengths to strings of some fixed length, where strings are sequences of some elements. This function should behave like a random function. So ideally, when proving something about hash function, sometimes we actually can replace it with a random function. Random function is such a function that its result for every possible input is uniformly distributed independently from all other inputs. So for every possible input value, it should provide some uniformly distributed hash value. And also B, the set from which input and output sequences are taken, can be the set of all bytes or bits. And in fact, many hash functions, for example, MD5 or all SHA functions, are defined in terms of bits rather than bytes. So it is possible to use those functions to hash sequences of bits which are not a whole number of bytes, but only a small number of implementations actually support this. But yeah, for this reason, if you look at the definition of this function, you can see, for example, that they use message length as the number of bits because, because they are designed to support any number of bits. But some newer hash function like Blake2 or Blake3 actually only support hashing a whole number of bytes because that's what most users need. So it should be like random, it should work like a random function, and if it were a random function, it would be very secure. Like, for example, a value of a hash function won't give you any information except that if you can guess the exact message that was hashed, you can try to hash it again and you will get identical value. But actual hash functions have some different security properties or don't have. So the first one of them is the first preimage resistance, which means that if you are given only the value of a hash function, then you can't find any message which has the same hash. And this is a property that pretty much every hash function actually possesses. But there is also second preimage resistance, which means that if you have some message, it should be difficult to find a different message which has the same hash value. And then there is collision resistance, meaning that it should be difficult to find any two different messages which have the same hash value. And the final one is indifferentiability, which is pretty complex. So it means that hash functions behaves in a certain sense like a random function, which all hash functions are supposed to do, but many don't. So the mathematical definition of indifferentiability is pretty complex, but also when some older functions were designed, the indifferentiability was not taken into consideration, so those older functions lack this property by design, unlike the part where MD5 and SHA1 lack collision resistance. They were actually designed to be collision resistant, but later they were broken, and some ways were discovered to actually find collisions for those functions, but they are still considered pre-image resistant. And so these four properties are ordered from weakest to strongest. So if a function doesn't have first pre-image resistance, then it won't have any of the later properties as well. And if a function doesn't have second pre-image resistance, then it won't be collision resistant. And if a function is not collision resistant, then it won't be indifferentiable. So later hash functions provide strictly more security than the earlier ones. And so how hash functions are implemented? Most hash functions are, pretty much all hash functions are based on a so-called one-way compression function, which is a function that just maps some longer fixed length input to a shorter one. This is because those fixed length functions are easier to design, and it's easier to prove their security properties. So to turn a function with a fixed length input into a function with a variable length input, there is a so-called Merkle-Damgard construction, which basically pads the message, splits it into blocks, and passes each block to a compression function together with the result of the previous call. So there is some initial value, which is called initial state, and then it is updated with the message blocks. And the final state is the resulting hash value. And the message needs to be padded so that its length is multiple of block size. And this padding should be designed in such a way that different messages result in different padded messages, so that there is no collision because of padding. So for example, if you just pad the message with 0 bytes, it won't be a good padding, because different messages which differ by adding 0 bytes to the end may result in identical padded messages, and then the hashes will be also identical. So many hash functions solve this by appending message length to the end, but there are other approaches. Unfortunately, this construction has a weakness, which is length extension attack. So if you have a message, you can, if you know just a hash of some message, but not the message itself, you can pad it, then append anything, and then take the result as a new message, and you can compute its hash. So how do you do this? You know the output state of processing the initial message and the padding. So you can take this state, apply compression function a number of times, and then you'll get a new state. Piotr, do you want to ask something?
Yes, I wanted to only ask, why is that? What could happen if those kind of attacks are allowed? Like,
Yeah, so it depends on what you are using a hash function for. This attack doesn't violate collision resistance, so if that's all that you need, then you're fine. But sometimes hash functions are used for authentication. For example, in some protocols, to authenticate some request, you need to pass a hash of some secret key plus that request. And for this kind of usage, length extension attack actually breaks its security because you can append some additional data to the request and compute. So if you can intercept the original request with its hash, you can append some data and make a modified request with a hash that you also know, even if you don't know the key. So also this is one of the way in which hash function materially differs from random function, because with a true random function, you can't do this. One of the functions which has a different structure is Blake3. Unlike most functions, it has a built-in Merkle tree. So it works as follows. It split the input into chunks of length of 1 kilobyte. Each chunk is hashed normally, sequentially, and then there is a Merkle tree on top of those chunks. So this is done to improve its performance, because different chunks can be hashed in parallel, and official Blake3 implementation uses SIMD to actually do this. It can compute up to 16 instances in parallel. So if you have at least 16 kilobytes of data, you can actually get the full performance. Yeah. So, but pretty much every other hash function uses simple sequential structure. Yeah, so the next thing I wanted to talk about is Merkle trees. We use Merkle trees a lot. So a simple structure, just pair up the values, concatenate the hashes, then pair up the resulting values, concatenate the hashes, hash, all of this. What's good about Merkle tree? The first thing is that it is as collision resistant as the hash function itself, so only a single root hash can be used to commit to the entire set of tree values, and you can't make a different set of values which will have the same hash. Another thing that is specific to Merkle trees is that it is possible to provide short proofs of a specific element. So suppose that you want to prove that the value D2 is in a tree with a given root hash, you need, in this case, to provide only 3 different hashes, and you also need to provide information about which hash is the left child and which one is right child, but this is very small amount of information. Then to check the hash, the verifier needs to compute the hash of D2, then concatenate it with the hash of D3 and hash that, then concatenate it with another hash and hash that, and then repeat this again, and then the resulting hash must be equal to the root hash. Unfortunately, this trivial implementation of Merkle tree is not secure, so depending on which values are possible as leaves, it might be possible for an attacker to prove that some different value is present in the tree, which wasn't included in the list of elements when the tree was created. So there are two attacks. One is extension. So suppose that one of the data elements can be controlled by the attacker to some extent, and they can make it look like a concatenation of two hash values. Then they can construct a proof that the preimage of one of these values is actually a tree element. So what they need to do, they need to somehow make the value d2 in this example to have the same length as a concatenation of two hashes, and they need to know a preimage for one of those hashes, either the first one, like in this example, or the second one. And then they can append this hash to this proof to make a false proof, then some potentially arbitrary value is present in the tree. And the second attack works in the opposite direction. So you can take an internal node and try to make a proof that this node is a leaf node. So you just truncate your proof, remove one of the hashes from the end, and you get also a valid proof for some value which is not actually in the tree. So how to defend against those attacks? There are two approaches. One is to make the height explicit. So for example, one can make the tree, all leaves in the tree to be at the same depth, and then include this depth in the header somewhere next to this the root hash. And then the validation procedure must actually make sure that the number of hashes in the proof is correct. There are more complicated ways. For example, if the depth is not the same everywhere, but the tree has some fixed predictable structure, and again, whoever is verifying this proof has the necessary information to check that the proof ends at the right position, exactly at the leaf, not before and not after. And the second approach is to disambiguate the internal nodes and the leaf nodes, so to make sure that they don't have identical serialization. For example, it is possible to prepend the byte to each node, like prepend byte 0 to internal nodes and byte 1 to leaf nodes, or do disambiguate them in any other way. For example, in many cases, a leaf node cannot have the same length as an internal node, and this is enough to prevent this attack, because now it's not possible to misrepresent one for the other. But this is something that should be considered, because in NEAR, when I looked, I didn't find any explicit countermeasures against those attacks. But on the other hand, I couldn't find any place where it can be exploited either. So pretty much everywhere, the length of the leaf item cannot be exactly 64 bytes, and the leaf of an internal node is always 64 bytes because it's just a concatenation of two hashes. But maybe if we introduce some other hash tree, it might be vulnerable to this kind of attack. So if you are designing any sort of hash-based data structure, you should be aware of this and check if it can be attacked in a similar fashion. And that's it. Do you have any questions? No questions? Then thank you for watching.
I mean, so what are the what are you planning to do next? Do you have any other ideas? What are the possible improvements, or what else we can investigate?
Improvements for what?
I mean, are there any other hash functions that could be used instead of the one that you mentioned?
Used where? Like, are you saying about using a different hash function in near?
Yes, like have considered using different ones and.
So currently we are using SHA-256 mostly, and I'm thinking about switching to either Blake 2 or Blake 3.
Are there any other besides Blake hash functions besides Blake 2 or Blake 3 that actually meet all those properties?
There are many functions that meet the security properties if you are talking about this property.
Yes.
For example, all SHA-3 candidates are actually meeting all those properties because this was one of the design goals for SHA-3, and I'm not aware of any of them being broken, but Blake 2 and Blake 3 are the most popular of the newer hash functions, and I don't see a good reason to use any others. I could consider other function if they were substantially better in some characteristic than those popular hash functions, but I'm not aware of any other functions that are significantly better for our use cases.
Okay, that makes sense. So basically, you have chosen one that's currently seems to be the most popular. So what's the difference between the Blake 2 or Blake 3?
Blake 3 is newer. It is designed so it has better performance. It's designed for parallelism, as I explained. But in terms of security, they're pretty similar. Also, because Blake 3 has a built-in Merkle tree, you can prove that some sequence is a substring of a hashed message without providing the entire message. Yegor, do you have a question?
Yes. Have you thought about, suppose we want to change our hash function? What happens with challenges on the border of changing? I guess there wouldn't be any problem, but if you thought about it already, can you say something about it?
I think it's the same as with any protocol change. So if you are challenging a block that was using a different protocol version, then you have to validate it using that protocol version that was in effect at that time. Any other questions? Well, thank you for watching.
Yeah, thanks.